Right. Okay, so we start the third day of the school. We are very happy that you accepted our invitation to participate in this activity. Let me introduce the speaker to the audience. So Professor Zuzanna Zolek is coming from the Warsaw University of Technology in Poland. The webinar today will be on materials based on natural resources for printed electronics. So the focus of the lecture will be developing devices using natural materials based on natural resources for printed electronics, mainly on paper. A few words about the speaker. She's a professor, associate professor with a PhD in chemistry science from Warsaw University of Technology. She is the Associate Dean for Student Affairs, and she is responsible for leadership of the Department of Printing Technologies research areas as a head of department in the paper making and printing BS, Bachelor and Master academic programs. She is also one of the creators of the current paper making and printing BS program, which was launched in an upgraded version in October 2019. Her research includes the surface chemistry of plastic films, the interaction between printing inks and printing surface, and printing on plastic films with solvent and water-based printing inks. Currently, her research is focused on the development and properties of starch-based materials as novel packaging materials. Furthermore, she has led two research projects financed by external sources, and the Foundation for Polish Science granted her a scholarship for young researchers. She is a co-author of 40 articles. Over 15 are in the printing technology area. So thank you very much, and the floor is yours.
Thank you very much. Today I will show you a webinar about materials based on natural resources for printed electronics. But before I begin, I would like to say hello to everybody, and also I would like to thank the organizers for the invitation. It was a pleasure to join second online Emerge Project School as a speaker. My name is Zuzanna Zolek. I'm from Warsaw University of Technology, from Faculty of Mechanical and Industrial Engineering. Here you can, on the right side, you can see our main building. The Warsaw University of Technology is one of the oldest universities and one of the biggest and best technical universities in Poland and also in Middle Europe. It should be highlighted that printing program for bachelor and master students is only at our university and also in Łódź University. Łódź University, University of Technology. And also we are probably the only one department which is involved in the research regarding printed electronics. So on this slide, I show you the plan of my presentation. First, I would say a few words about e-waste. Then I will discuss the difference between bio-based and biodegradable materials. Then I will switch to nature-derived materials and their applications for printed electronics, especially cellulose, starch, and synthetic polymers based on natural resources. And finally, I will sum up my presentation. So everybody knows the term Green Deal. Everybody heard about Green Deal. This is a set of policy which are accepted by the European Commission with aims of making the European Union climate neutral in the future. Also, e-waste have some specific rules. So waste from electrical and electronic equipment are known as a WEEE or e-waste. E-waste contains a mixture of materials. Some of them are unfortunately harmful to the environment, and some of them can cause major environmental and health problems if they aren't managed properly after their end of life. So there are some rules in the European Union on treating the e-waste, to contribute us towards a circular and more sustainable economy. Today, in European Union, more than 13 million tons of electrical and electronic equipment are put into the market. Nearly 5 million tons of e-waste are collected, and 11 kilograms of e-waste is collected per person. Okay, sorry, something is not working, but waste from, okay, but we have to know that some of printed electronics applications are not listed on WE products. Those are interactive posters. Those are pamphlets, smart books, smart packaging, and smart textiles. So what we can do to switch towards more sustainable, more green printed flexible electronics. Firstly, we have to know that the accumulation of e-waste is a pressing global problem, and the number of e-waste is rapidly growing problem worldwide. Printed electronics may offer us some sustainable alternatives to conventional electronics, and using more green, more environmentally friendly, more biodegradable or biocompatible materials, we can make electronic less harmful to the environment. Current efforts are to choose conductive inks or composites for the purpose of printed electronics over polymeric substrates, which often are fossil-based, are prepared using some organic harmful solvents, and at the same time can cause us, for example, microplastic, which is a big problem for our health and environment. So instead of choosing fossil-based materials, fossil-based plastics, we can choose some materials which are less toxic and doesn't cause any harmful in our life or humans or environment. So on this figure, you can see on the left the focus is on wearable and flexible devices that can monitor physical strength of human. We can have different e-wearable electronics which monitor our health. At the same time, we can use nature-derived biomaterials from various resources. For example, we can use cellulose from leaves or trees. We can use clay from volcano. We can use alginate from algae or silk fibrous from silkworms, and also hydrogen from, for example, exoskeletons. It's the prop here. But before we go to the bio-based and biodegradable materials, we have to understand the difference between them. Bio-based plastics are fully or partially made from biological resources. But when we have a term bio-based, it doesn't mean that the material is biodegradable, because biodegradability is the ability of the material to degrade in the natural environment through the actions of microorganisms such as bacteria, fungi, enzymes, and many more. In this process, as a result, we get carbon dioxide, water, biomass if the process is with presence of oxygen, or we can get methane, water, or biomass if the process is without excess of oxygen. So, biodegradable plastics are certified according to several standards, defining precise condition for composting. So, in general, the product should disintegrate within during composting process within 84 days. So after 84 days, the product should be degrade and have no negatively influence on the compost and should support the plant growth. We have to remember that when we use a biodegradable product, all the contaminants of this product should be biodegradable. So when we use biodegradable, for example, bottle, the print should be also biodegradable. To decrease the usage of conventional fossil-based plastics, bio-based and biodegradable plastics were introduced to our lives. This figure shows us the classification of plastics based on their origin. Are they petroleum-based or bio-based? Bio-based, or are they biodegradable or non-biodegradable? So we have bioplastics, which are biodegradable, and they might be produced from bio-based resources. We have bioplastics, which are biodegradable, but they are produced from petroleum-based resources. The third group of bioplastics are non-biodegradable materials or partially biodegradable plastics, which are made from bio-based monomers. And the last group, conventional materials, conventional plastics, for example, PET, PP, which aren't degradable and are harmful to the environment and cause problems of microplastics. So the ideal biodegradable material life cycle is that we grow a plant, then through the process of extraction, refining, and fermenting, we manufacture our bioplastic, which we can then use, and after usage is utilized as a organic waste, then it is composted, and after that we can again harvest our raw materials for the preparation of our product. Those kind of products can be certified industrially according to the European standard 13432, and they are presence of a seedling logo, proving that this material, this product, is compostable under controlled conditions such as temperature. Typically, it is 55 centigrade, moisture, and time. However, the temperature in our home composters is usually lower and less stable due to the smaller volume of organic waste which are involved in the composting process. So there was a need of development of home composting logo, which you can see here, and guarantee the complete biodegradability of the product in the home composter. So now I will tell you about nature-derived materials, which might be intended for printed electronics. The overall sustainability trend shifts us towards nature-derived materials which have lower carbon footprint. For the purpose of this webinar, I have divided the nature-derived materials into 4 different groups. Those are polysaccharides, proteins and peptides, synthetic polymers, and combined materials, which can be a kind of material with all of the other groups. On the next slide, I will discuss especially polysaccharides a little bit wider. Polysaccharides are a class of biological macromolecules which are built from repeated units of monosaccharides, such as glucose, which are linked by glucosidic bond to form linear or branched chains. Polysaccharides are the most promising alternative to synthetic plastics due to their easy accessibility, high abundance, low cost, and also at the same time they are non-toxic, biodegradable, biocompatible, renewable, and environmentally friendly. In this slide, you can see the possible application of polysaccharides-based materials for smart packaging. Due to the abundance of polysaccharides, due to their chemical structure and the number of reactive groups, also a wide range of their molecular weights, we can apply them for many, they can be processed in various target products, including sensors, sensors, indicators for smart packaging to give the customer the information about the freshness of the product, or data carriers, and those materials can be successfully applied. Cellulose is a great candidate which can replace synthetic polymers as a flexible substrate for printed electronics. Cellulose is bio-based and biodegradable, and also due to numerous functional properties, it can be used for printed electronics. The cellulose is one of the most abundant bio-based materials on our planet. Cellulose products which we use every day is paper or cardboard, and those products have been already studied for flexible electronic applications, especially some printed devices. At the same time, cellulose in form of the paper or cardboard can be printed in various processes. For example, roll-to-roll processes such as flexography, screen printing, inkjet print, digital printing, and etc. And the only limit of paper substrate for printed electronics is the poor transparency of or non-transparency of the paper, or barrier properties against, for example, water or solvents, and quite big surface roughness in comparison to plastics substrate. So, cellulose and cellulose derivatives can find numerous applications for printed electronics. Cellulose nanocrystals are crystals of cellulose with a very low end diameter. They have less than 30 nanometers and length lower than 500 nanometers, but they have a shape or like nanocrystals. We have nanofibrillated nanocellulose or microfibrillated cellulose, which is elementary fibril of cellulose, measuring up to 20 nanometers in diameter and 10 micrometers in length. Those materials are prepared by acid hydrolysis of cellulose. Then we have bacterial cellulose, which is a source of pure cellulose and might be synthesized in the process by some specific bacteria. The last group of cellulose derivatives is some chemical derivatives of cellulose, carboxymethyl, methyl cellulose, and hydroxypropyl cellulose. And all of them can find applications in various e-wearable or e-devices. For example, human monitors for a skin, which are based on nanofibrillated cellulose and carbon nanotubes, or we can make a substrate and nanocellulose paper for printed electronics. We can also produce some conductive ink based on ethyl cellulose, or we can do paper substrates for RFID antennas, and many, many more. Another polymer which is also abundant in the environment is starch. The starch belongs to the family of carbohydrates, and it's produced by plants as a food reserve. It should be highlighted that we can harvest starch without destroying the plant. Starch mainly consists of two major polysaccharides. This is linear amylose and highly branched amylopectin, and the number of amylose and amylopectin depends on the plant source. Commercially available starch is mainly derived from plants such as wheat, rice, corn, potato. In European Union region, the starch is mainly derived from potatoes and wheat. Worldwide, corn starch is produced, nearly 80% of starch is produced from corn, and in the United States of America, they produce most of the starch worldwide. Starch materials are attractive due to their biodegradability and availability from renewable resources. Also, they are cheap. Starch is formed in nature, so such materials are bio-based and might be biodegradable. The filmogenic properties of starch are known since 80s of the last century, and they are now a topic of intensive research. In our laboratory, we have developed some materials, environmentally friendly, which then we have used for printing. So they can be used for biodegradable, environmentally friendly packaging, and also at the same time, they can be used for printed electronics. For example, we have obtained films with good quality, with a quite a long lifetime, and also after few years of storage, they still have acceptable properties. The only thing that changed was the color. The old ones are more yellowish than the fresh ones. But also at the same time, they have a suitable elasticity, about 20%, which might be valuable for example, flexible electronics application when we use those materials for e-skin electronics or some devices. Okay, sorry, I just wanted to go to the next slide. So we have also presented some cytocompatible and electrically conductive structures of nanocarbon water-soluble composites based on starch film. And how you can see on this slide, they are flexible and also in the future we would like to make them more elastic. The next polysaccharides, which is also abundant in our nature is chitin. Chitin together with starch is the second abundant polysaccharide. Chitin is composed of repeating units, and chitin exists in cells of arthropods, such as crabs, some insects, fungi, or also shrimp. Chitin is a rigid and crystalline polymer, but it can be easily formed by the acetylation process from chitin into chitosan, which is soluble in acid solvents. So chitosan can be used as a material for some substrates. And it is worth to mention that chitosan can be easily enzymatically biodegraded by the human body, mainly thanks to the activity of some enzymes, especially lysoenzyme. And also chitosan can degrade in the environment up to 10 days. So the carbon footprint of chitosan and chitin is very low. But also nature can be a great source of molecules that they can be combined with other materials, or then can be used as a source for to approach to develop synthetic polymers. So there are some bio-based polymers which are derived from nature and renewable resources, such as plants, microbes, or forestry feedstock, and we can prepare eco-friendly materials. Those synthetic materials, which are polymers based on natural raw materials, is PLA, polylactide, and its derivatives, polyhydroxyalkanates, and polybutyl succinate. Oh, sorry. Okay. PLA, polylactide, is a biodegradable aliphatic polyester, and it is most technologically advanced biodegradable polymer. This material is thermoplastic. It is known from the 20th of last century. It was invented by Wallace Carothers, who invented also nylon, but it wasn't commercialized on a large scale in this time. But with combining of various monomers, we can form various PLA derivatives, such as the polydilactic acid, poly-L-lactic acid, or polylactic glycolic acid. For printed electronic, PLA can be applied in numerous applications. For example, we can use PLA as a conductive filament for graphene-based filaments for FDM 3D printing technology. It can be applied as binders for conductive inks, or also spray, or we can make PLA-based conductive paste for screen printing. So the last question is BioPET, scam or marketing. BioPET is a material obtained from renewable sources based on plant raw materials, but it's not biodegradable, either compostable. PET, is not biodegradable. The same is with BioPET. The bio doesn't mean that BioPET is biodegradable. It just shows you that the source of raw materials to produce plant bottle is instead of using fossil-based raw materials, we use nature-derived raw materials. The final product is still the same PET we know from bottles. The bio prefix not indicates us whether the product is biodegradable or not. So when we see some product which is bio, it doesn't mean it's really biodegradable. It doesn't mean it is for example, low carbon footprint. So before I will end my presentation, I would like to do a sum up. So what we can do with the problem of waste in our life. Firstly, we can replace fossil-based substrate material with some biopolymer alternatives. We can choose more sustainable functional inks without heavy metals and preferably based on biorenewable raw materials. And last, we can reduce the impact of our products by implementing eco-design and circular design through minimization of material usage. And the last, we can use bio-friendly green materials. We can also educate us, our children, students, in the topic of proper management, waste management, material management, and we have to remember to recycle the materials in a proper way. So here are some references I was using for my presentation, not all because I forgot to add something, but thank you for your attention, and thank you that you were still listening to me. And do you have any questions? Okay. No questions?
Thank you very much. Sorry, there is some work outside.
I don't hear you.
Yes, sorry, there was some workers outside my office. There was some noise. Thank you very much for the acceptance to participate in our school. I think we have enough time for some questions. Let me check.
Oh.
Let me check the chat.
I
have already some questions. Let me read the questions. So, Mr. Paul asking, do you have any information on the percentage of silicon extracted from e-waste, if any?
No, I didn't check this information. the main problem with the e-waste is that the recycling process is not easy, and also some of the European countries takes the e-waste to the landfills, and some unfortunately send them to the poorer regions of our world. But I don't have this information.
Okay, thank you very much. Another question is, what is the norm to certify a polymer as a compostable plastic? Is there any definition or?
Okay, I will try to go back with my presentation.
Yes.
One moment, please, okay? Oh, here it is. The norm for compostable materials is European standard 13432. This is the standard, is so related with biodegradability on soil and water. In this standard, European standard, the total degradation of the products is 84 days. So after 84 days, you have to this product in the compost. And then you get this European standard, yes, the seedling logo. But in this standard, there are strict rules on the process conditions. So the temperature, the humidity, and the temperature, humidity, and water content, never mind, are strictly defined. And so when we put the product in the home composter, which has a little bit different conditions, we weren't able to get the total biodegradation process. In my opinion, the ISO norm for the biodegradability on soil and water are a little bit different. It depends because you have few ISO standards regarding this biodegradability problem.
Okay, thank you very much. Another question. How can one mitigate the hydrophilicity and swelling of cellulosic substrates without using siloxane chemistry? Is cellulose hornification a good option?
Okay. Cellulose as well starch materials are hydrophilic, so we have to increase the hydrophobicity, yes, of these materials. I don't know, you have to try if cellulose hornification might be a good option. The best way to do is to, for example, do to check wettability by water contact measurements.
Okay, thank you. Another question. How can we decouple the use of cellulose, which has all the biodegradable properties that we like, from the industrial processes used to isolate it? Processes which use lots of strong acids, bases, to separate out the cellulose from hemicellulose, etc. No, no. Is it clear?
Okay.
I'm not an expert in the field.
You can do the solution of not acid bases. In the bases, you have in the basis solution, and then you can separate the cellulose from hemicellulose and lignin. This is the solution should be 17 and 0.5% of hydroxyl, oh my God, I forget, sodium in water. You can write me email.
Yes, for further
My
discussion.
email is on the presentation. I will write you all what you have to do.
Okay, thank you very much. Another question about the long-term stability and reliability of devices using natural resources and natural resource-based materials, especially in varying environmental conditions. About the stability, yes.
The materials such as starch, for example, and cellulose, they have a poorer stability than normal fossil-based materials. In my opinion, we have to be prepared that they will be less stable and they have a shorter life in comparison to the normal fossil-based materials or devices. We have to choose what we want, or we are more sustainable, more greener, or we want to have something which have a longer life.
Okay, thank you. Another question regarding the e-waste. According to the applicant here, the replacement of e-waste by biodegradable materials can increase the concentration of carbon in nature, which can present toxicity. What is your opinion about that?
Okay. Yes, that's true. We can think that applying more biodegradable materials, we can increase the concentration of carbon dioxide in our nature, which then makes that on the planet is hotter than it used to be. But I think we should calculate the life cycle analysis on this topic. So we have to see, is it better to use conventional materials, or is it better to use biodegradable materials instead of fossil-based? And then we can calculate, we can choose which options generate less carbon and have a lower carbon footprint.
Okay, thank you very much. I think we have enough time for questions.
Yeah, okay.
It was the last one, but we have another question right now. Do you need either the compostable certification and the biodegradability for printed electronics, or can be one of these? I mean, you need both of them or one of them, because the time frame is different. 84 days
okay.
for compostable.
Seedling our logo is mainly for the packaging. I just wanted you to see the difference between biodegradability, bio-based materials, bioplastics, because these aren't interchangeable terms. So 84 days is mainly for biodegradable materials, which are dedicated for example, packaging. So we have a packaging, we throw away the packaging, and then we see there's nothing left. So for electronic devices, we can, depending on the application of this device, yes, because we have some for short time use, and then we have some for long time use.
Okay, so is there any other question from the audience? I think we had a lot, we have many of them. Otherwise, I would like to thank you again for your acceptance to participate in our school.
Yes, it was a pleasure, but I just wanted to say that the questions were more stressful than the presentation. But it was really a pleasure to join you today.
Thank you very much. So I think now we have...
very much.
Yes.
Bye-bye.
Thank you, thank you. Now for the audience, I think we have 10 minutes till the next speaker, so we have to wait a little bit. We are waiting also the speaker to join us. So in a few minutes, he will be here. So let's wait a few minutes. Thank you. Great. I think Professor Mendes joined the room. Professor Mendes?
Yeah, can you hear me?
Yes.
Good,
Great.
perfect. And now let me see if I appear. Can you see me?
Yes, perfect.
Good,
Also,
thank you, Lou.
you can try to share your screen just to check that we can see your slides. Great. Also, you can put it in full screen. Yes.
Can you hear me now?
Great. Everything is perfect. So
Good,
let's
good,
wait.
good.
Just to follow the program, let's wait a few minutes.
Yes, yes, yes. Okay, so thank you very much for the invitation. It is really a pleasure. And you have a lot of people here, 80 participants.
Yes. Thank you for accepting to participate.
Let me. Okay.
Starting in 2 minutes.
How much time do you want me to talk? Because I can accommodate.
I mean, the duration is around 45 minutes, and then we have time for questions. So 45 minutes.
Perfect.
Perfect.
Yes, yes,
And then
yes.
the audience can ask some questions.
I can accommodate between 20 minutes and 3 hours, more or less.
I will interrupt you, no worries. Which are the people we have there? Which backgrounds? Physics, chemistry, material science? From all the fields, their background is covering all the fields. I mean.
Okay. And all of them have experience with printing technologies?
I guess most of them.
Okay, because I will make an introduction.
Okay, nice. Maybe I can start the introduction of the speaker. So thank you very much for participating in our school. So Professor Lanceros Mendes will speak about sustainable ink for screen printable sensors and actuators related to IoT and Industry 4 applications. A few words about his profile. He's a professor at BCMaterials in Spain, in Basque Center for Materials, Applications and Nanostructures. He is the scientific director of the institution. He's an associate professor at the physics department of the University of Minho, Portugal, where also belongs to the Center of Physics. He graduated in physics at the University of Basque Country in Spain and obtained his PhD degree at the Institute of Physics of the Julius Maximilians University, Würzburg, if I'm correct, in Germany. His work is focused in the development of smart and multifunctional materials from sensors, actuators, energy, environmental, and biomedical applications. So thank you very much for the participation, and the floor is yours. Thank you very much.
Thank you very much, Konstantinos, and Sergio, thank you very much to the Emerge Network for thinking about me and for inviting me here. It is always a real pleasure to share what we do, because we are, as you would have seen from the other speakers, very motivated in what we do, and we truly believe that it is important, and we truly believe that it is needed. So, and this is what I want to share a little bit, the relevance of what we are doing and why this is very important for the next generation technologies, okay? That's why I will spend a while, about 10 minutes, just in the general context. I think that in this case is particularly relevant because either we have what we have to do in terms of performance and sustainability related to printing technologies, or we will have one or two big problems in the near future, okay? And that's why the important issues here is printable sensors and actuators that are absolutely needed for the next generation of technologies, and sustainability, which is absolutely needed for a suitable life in our planet, okay? And for that, let's start with the context. And the context is inspiring. We are about 8,000 million people on the planet, okay? A lot of people that want to have a very nice average standard of life, a bunch of people that need a lot of energy, a lot of people that need a lot of foods, that are contaminated water, and would have a complex relationship with the environment. And that's why, from the United Nations main concerns, energy, water, food, and environment are the main concerns for human population nowadays on Earth, okay? And this is always important to consider, because we do technology, we do materials, in our case, materials for advanced technologies that will be implemented, and which aim is to improve the quality of life of people, okay? And that's why this context has to be always taken into consideration. The second important issue is that we are in the middle, right in the middle, and that's why it is so important to be a young attendee, as you are now, in the middle of three revolutions. The biomedicine revolution, it is not the first one that we have, it's one among many. We have been always concerned on our health, and now technology helps a lot to live longer and to live better, okay? And it has been a lot of stress in the healthcare in all countries, because we are able to heal more illnesses for more people during more time. And that's why the health-related technologies have to become more active, more proactive, and more predictive. I say that because this is also very related with the last revolution, that is more important one. The second one is the Green Deal. That means that we realize that we are having a strong impact in the environment. And we know that the future technologies cannot be as the past technologies. In terms of materials, in terms of processes, in terms of energy use and the type of use that we need, they must be more sustainable. It is impossible to continue in the way we go, okay? But the most important one, the one that is going to define our time in history, probably, when 200 years from now people look back, what people were doing in the beginning of the 21st century, people will say digitalization. Digitalization of the economy, digitalization of the society, interactivity, every time, everywhere, on every issue. And this digitalization will have a profound impact also in the other two, in biomedicine and in the sustainability issues. Okay, and we are seeing already now, when I was a young PhD student, it is very interesting because it was about 1 million interconnected devices in the world, basically computers. Okay, now in my career that spans more or less 23, 24 years already, we have over 50 billion interconnected devices and increasing. And this is giving rise to the fourth, or maybe for some people already the fifth industrial revolution. The first one related basically with water and steam. The second one basically with electrical power. The third revolution already introducing the computer technologies, and the fourth industrial revolution basically production facilities with the Internet of Things. And we have everything ready so that it properly works. Basically, we have the highways for communication, okay? Basically the 5G that we are implementing everywhere nowadays. We have the systems that can handle this information. We have that in our pockets. We have that, as you see, in our computers, and I am able to talk to everybody in the world nowadays. So if we can share information everywhere, every time, what we need is information. And we have to gather this information. And this gathering of information is basically related with the full implementation, full-scale implementations of sensors, okay, to gather information, and to actuators, to actuate based on the information that we gather, that not always can be spoken as we are doing nowadays. And this is a true revolution, okay? This is a true revelation coming nowadays, and it is expected that by 2025, that means 1 year and a half, basically from now, the 9 settings related to the Internet of Things is valued up to 11 trillion per year. So it's a full revolution in how we live, home automation, smart living in the vehicles, autonomous living in the cities, smart cities, in the factories, automated factories, in the logistics more than in any other part, and so on. And again, what we need basically is to gather information. We know how to share, we know how to handle, and now with the internet, artificial intelligence even better, but we need this big deal of information, and then we need to react according to this information. That means we need an increasing number of sensors and actuators that must be located basically everywhere. And sensors and actuators are based on materials. And there is no revolution all over the history of humankind that has not been based on new generation of materials and the corresponding production technologies. From the Stone Age to the Bronze Age, to the Age of Steel, to the Age of Polymers, okay? We have been always relying on materials for performing of these new technologies that help to have a different production technologies, different products, and different living standards, okay? And now we are doing these transitions in a faster and faster and faster way. I like to say this example. When we started writing, it was in the 3000 BC, and then we only invented the printing press 4,000 years later. From the time in which we invented the transistor to having internet everywhere, it was basically 20-25 years, okay? Everything is speeding up. And second, the materials we use and that define a given technology, are a given period of time, a given revolution, are not the one that we use at the most. As you see, in the age of polymers, okay, that is basically by the 60s, what we use at most was metal, okay? And even in the Stone Age, we used basically as much polymers as a stone, okay? Are the materials that make the difference. And the materials that make the difference in this revolution that we are having is the materials that we design, the smart and functional materials. The materials that we design with specific properties for specific actions or for specific interactions. And that's why we are in a fabulous time nowadays for being a physicist, chemistry, material scientist, chemical engineer, and so on, because we have the ability to design materials with specific properties and properly implemented in whatever technology we want. Okay, and this is the time that is making us move forward towards what people say already, Industry 5.0, and this super smart society in which information flow, in which interaction flows. But till now, all revolutions have been basically based on performance. Let's have high performance materials. Let's have high performance industry. Let's have high performance products. And this cannot follow now anymore, because now we have to check out performance and sustainability. Okay? For which areas performance is the main parameter, but whenever it is not needed, let's try to keep with the most sustainable technologies to have a lower environmental impact. And this is particularly important in the area that we are dealing with, okay, in the area of sensors and actuators and printing technologies, okay? Because, and this is a very important saying, so nobody can go back and make a new beginning. Anyone can start over and make a new ending. And the new ending we have to do is a more sustainable way. And this is not activism, this is not a political statement, this is a real need, okay? A real need for which we have responsibility, okay? And in fact, when people look at the goals for the millennium, the sustainable goals for development, from the 17, almost, 7 are directly related to materials, but from the another 3 are indirectly related to materials. So materials and technologies are the basis of sustainable development. And this is more than ever important in the transition to the digitalization, because we need a new generation of materials. We need new fabrication methods. We need materials that are more interactive. We need materials that are more efficient. We need materials that are more sustainable. But more important, the digitalization has to be sustainable. Because imagine the thousands of millions of sensors that we are going to implement everywhere in our body, in our clothing, in our rooms, in our cars, in our city. What would happen if they are not sustainable? If they are not designed to be recycled, to be reused, to be biodegraded, okay? We have an incredible amount of small things, many of them, even probably with nanoparticles that we do not have knowledge about nano safety, both from the environmental point of view or from the biological point of view, everywhere we spread around the world with no clear end of life management. The e-waste, that is a problem already, will be a joke comparing with this spectrum. But we are on time to take advantage of the knowledge we have and to make this transition more sustainable. It is not impossible, of course it is close to not possible, but this is what we are here about, to do these technologies that actually can improve our living standard without degrading our environmental standard. And for that, we need this new generation of materials, especially for sensors and actuators, okay? Materials have to be smart, materials have to be multifunctional, materials have to be sustainable. From the origin, okay, refuse is the most important issue for sustainability with things we do not use. Then we have reform, then reduce, then reuse, and then recycle, okay? Very clear which material we can use, whether we cannot use. And second, whether material we can use that we can use many times, and whether we can use that we can use only one time. Only one time material has to be sustainable and bio-based and degradable. Otherwise, it will be a strong environmental burden, okay? What is a multifunctional materials? It is very clear for everybody. It's a material that have more than one function, okay? And there is a contribution to sustainability, even if material it is not, okay? If we have a material that it is self-cleaning, for example, in the car or in our windows, even if the material itself it is not, the application is, because we do not need to clean so many times and we are not going to use so many chemical products. Okay, so sometimes sustainability, that is a big word, it is not necessarily in the material that we use. One example, and this is not publicity, probably it is better Samsonite luggage that you can use the whole life, okay, with a synthetic polymer, but when that is biodegradable and you have to change every time that you make a trip, okay, because then you have to recycle the material, you have to produce again, and so on. So in all this life cycle assessment, we have to take account everything, the materials we use and the end of life of the materials. But self-clean is a good example. Self-healing, materials that whenever they have a problem, they auto-repair, particularly important in our mobile phones, but also in many of the applications we have, so that we don't have to change, especially electronics, so many times as we do nowadays. And the most important one, self-sensing materials, so that they can provide information about themselves, about their environment. And in these self-sensing materials is where it comes the second category of smart materials. Basically, stimuli responsive materials, okay? Materials that not only play the function, for example, as a packaging, okay, but also provides information on what is in the packaging or in which environment this package was. If we do not introduce sensor, but the material itself, the package itself has these sensing capabilities, we are saving a lot because we don't have two products, we have only one. And if it is sustainable and smart materials, we are even having this reduced environmental impact. Smart materials, there is a huge variety of them. Basically, materials that react to one physical or chemical variation of the environment and provide a given signal that allows me to react. Most of the time, this second signal used to be electrical, because electricity is the force of nature we master at best, and then we can read up, we can calculate, we can communicate, but many times can be optical, can be a specific bioactivity, can be mechanical, whatsoever, okay? One of the things that we are going to see a little bit more along the talk, the 25 minutes we have rest, are electroactive materials. The most typical example, piezoelectric materials. I have a materials, I apply a force and develops a voltage. That means that I can measure force, impact, deformation, whatever it is, through an electrical system that I can then provide this information to whatever databases or system it takes. Or the opposite, okay? I can apply an electrical signal and the materials provides a force. In the first case, I have a sensor. In the second, an actuator with the same material. What does it provide for sustainability, even if the material itself is not sustainable, because it is a, I don't know, fluorinated polymer, okay? Okay, if it has durability, what it provides is integration and multifunctionality. It is simple, it is lighter, it has higher performance, and it can substitute many of the components of an actuator, many of the components of a sensor, and also the structural support. So there are many ways to go to a more sustainable future, and it has to be considered in each application. And now, how do I reach these materials by design? Okay, one thing is clear, is by synthesis. In the case of polymer, for example, in this case, I have a fluorinated polymer, PVDF, that is electroactive, is piezoelectric, and I can improve or decrease, in any case, tune this piezo, pyro, or ferroelectricity by making some chemical engineering by substituting some fluorines, but a group of fluorines, or by doing copolymerization with different entities. It is possible, it is more difficult, and the variety of effects that we have are not so big. We have another possibility, and now we are approaching to the inks. We can do hybrid composites, okay? We can, for example, introduce piezoelectric nanoparticles, titanium dioxide, barium titanate, sorry, in a polymer matrix. and I have a piezoelectric composite. And this is something I can convert into an ink for printing technologies. Or polymer and non-magnetic. I can introduce magnetic nanoparticles, and then I have something that I can print that is magnetic. Not only, it's also magnetostrictive. It can serve as a memory. Or I can introduce semiconductors. I have thermoelectric effects. Or also semiconductor quantum dots. I have photochromic, thermochromic, and so on. Okay, this is great. It works. But for these millions, trillions even, of sensors that I am going to place everywhere, even if it works, it has problems. It has nanoparticles. And nanoparticles, we do not know yet. Nanotoxicity in terms of human toxicity and environmental toxicity. I don't want to say that they cannot be used, but we have to be carefully until we know exactly what can happen. Okay? Then we have all these things, then it is not enough. Okay, material science is a science that has evolved to produce materials that can be applied. And I have been talking about material properties, but now I need fabrication processes so that I can process in a given geometry and I can get a product. And this is where it appears additive manufacturing technologies. First of all, because it's a sustainable technology from the beginning. Why? Because it is additive. It is not subtractive. In principle, everything that I get there is what I get in the final application. I have not so many residuals. Even if I have solvents in many of the technologies of additive manufacturing, I solvent-based, but in principle, I can recover them. Okay, so this is very important. And that's why it is also increasing so much the market of additive manufacturing in all areas, in all typical printing technologies that we have. Okay, from digital light processing to direct metal laser synthesis, so on. Okay, so to put together these two things, additive manufacturing and smart materials is great. And it's great because of one thing, and I like this. Additive manufacturing is not new. In fact, for many, is the most important inventions in the last millennia. Okay, and I do believe it is. Okay, because invented by Johannes Gutenberg, it makes something what was amazing. Okay, before the printing press, it was 30,000 books in the whole Europe, more or less for 12 million people. So knowledge, it was restricted to a few people and specific places. A few years after the invention of the printing press, okay, it was already more than 12 million books and increasing. So the invention of the printing press was the democratization of knowledge. Knowledge, thinking, criticism, further evolution of technologies. And I like to put these things together because it's what's happening nowadays. We are using, again, printing technologies for the digitalization, for the Internet of Things, that is, again, the sharing of information and knowledge. And if it was invented 600 years ago, why it is not so important printing technology? We don't have this emerged network. Why we have so many European projects? Why do we have so many industries that are doing this now and increasingly too? Basically, because the materials we can print. Printing technologies obviously have evolved a lot, but not as much as the materials that we can print. Basically, we can print any kind of materials nowadays. Okay, we can print sensors, actuators, protective covers, personalized 2- and 3-dimensional structures. We can print small structures and we can print large, huge areas structures. Okay, and this is because we can now put, as I told you before, a suspension of active particles in a solvent or in a polymer mediated dispersion, and I can print from the melt or I can print from the solution a huge variety of materials. The most typical example is for printed electronics. I can print conductors, semiconductors, dielectrics, resistive, or any kind of functional materials. And I can print in any place, in any substrate, in flexible plastics, on metals, on glass, and I can print in any shape, in 1D, into 3D, in 2D or in 3D shapes. And if it is into 3D, then I can do the conformation, okay? That means that is a huge opportunity, the one we have here. And the most important even is that we are creating with this a new technology, because printed electronics, for example, but the same in other printing areas, it is not competitive with conventional electronics. Conventional electronics, silicon-based electronics, will be always more performant, okay? But we do not need high performance everywhere. As I say, for the trillions of sensors that we are going to have everywhere, that have been implemented in textiles, that have to be implemented in inks, that in the walls, in the floors, whatever it is, we do not need huge performance and huge miniaturization. What we need is, for example, large areas, flexibility, bendability, whatever it is, okay? And that's why it is so important to put this and create all these generation of products, all this generation of enterprises, of this generation of economic possibilities, of this generation of persons that are formed in the new technologies that will be demanded for the very recent future, and that we still do not have professionals able to deal with all this. Because we have a huge variety of printing technologies, many of them already scalable. Screen printing, group printing, flexolography, offset, inkjet printing, scalability is there, but it's complicated. And they are well evolved, still evolving, but each of them requires specific inks for specific requirements that they have, okay? They have requirements in terms of resolutions, they have requirements in terms of the shape that they can print, but all of this is basically mediated by two things: which ink I am going to use, viscosity, for example, sulfate tension, and so on, and where I am going to print that, okay? Because whenever we are going to print something for application, we cannot optimize a specific part. We have to optimize all of them at the same time. For a given application, we cannot develop a very good ink with a good surface tension, viscosity, particle size, and solid content, or specific solvent. This says nothing. I have to precisely prepare an ink for a specific printing technology that will be printed in a specific substrate. It has to be done at the same time, okay? Otherwise, the ink won't work, for sure. Either will not be printed, or will not have sufficient adhesion, or will break down into pieces, or whatever it is, what it is done. Because then there is another important issue in ink development, okay? Because the ink is something that we process in the fluid, but we are not interested in the fluid at all. We are interested in the functional properties of the solid part. That's why rheology and surface energy are very important, because viscosity, printability, and substrate characteristics, the wet properties, are issues related with processability. But structure, adhesion, conductivity, cohesion, surface properties, the dry properties, are the ones related with functionality. And that's why it's very important to follow out this process, to master this process, and know that the process has to work, because at the end we want the product. And inks, for example, I put here the example for inkjet printing because it's one of the most complex technologies that we have. Can be solvent-based, can be dispersions of particles, can be UV curables, can be based on polymer, but we have to have a jetable fluid, a lot of problems. The particle size has to be below 0.2 microns, the viscosity in this case has to be very low, below 12 centipoise, surface tension, always evaluation is poor. And typically inks become very complex. They have the functional materials, dispersing a solvent, we have to be a surfactant so that there is no aggregation of particles, viscosity modifiers so that we have the viscosity that is compatible with the material, with the processing technologies, eventual adhesion promoters so that it has proper adhesion with that. And this is complex. So as all the materials nowadays and all the process nowadays have to be sustainable, the simpler the better, the less competitive the better. Because there are no projects nowadays that has not to consider the sustainability issues. And one of these is the end of life. Okay, how I'm going to reduce the materials, how I'm going to recycle the materials, what I am going to do with the sensor after the sensor is not more working and it is not functional. And so, two words that have to be there, materials have to be sustainable by design and has to be also safe by design. Okay, and the less components you use, the better it is. Okay, even for controlling the ink requirements. Obviously, in terms of stability, viscosity, surface tension, non-flammability, no toxicity, okay, but also the compatibility. Many times we deposit several inks, several times, almost always in the area of sensor actuators. You have at least 2, 3, 4 layers. You need compatibility between the different layers. So non-corrosive, substrate compatible, because sometimes the substrate in the second layer is the first layer, not the substrate that I am going to, in which way I'm going to use the material. And then the restrictions by the specific technology and then of the specific use. Drop ejection, for example, in digital technologies, and printability. And for that, people have been developing a lot of inks, okay? A lot of things, very simple ones, basically dispersing specific particles in specific polymers. As I say, for piezoelectric materials, PCTs, barium titanate, they in either active or non-active polymers. I say active, that only helps to the printability, or polymers that also support the specific functional characteristics that I need. For example, PVDF is a piezoelectric polymer. If I put a piezoelectric material in a piezoelectric polymer, probably I have a synergetic effect. Okay? Piezoelectric, piezoresistive, variation of the electrical resistance with the deformation, either conductive particles in a conductive polymer or conductive particle in a non-conductive polymer along the percolation threshold, magnetism, magnetic particles in a non-magnetic polymer, because there are almost no magnetic polymers. Okay, and that's it. This is what people is doing. So how can we do this, as I say, sustainable by design and safe by design? This is the issue, and this is what a lot of work will be, and this is a very important area of research and activity, okay? First of all, the most important of the areas of sustainability that all are R's, okay? Refuse, reform, reduce, reuse, and recycle. We also think about recyclability, but recyclability is the worst, is the one at the end, is the one that also takes energy, okay? Is the one that also implies refurbishing of the materials through complex processes. The first one is the most important, refuse, not use specific materials. In the case of nanoparticles, if possible, at the present moment, it's better not to use. Sometimes we have, but let's restrict to the areas in which they are absolutely necessary. Second is reform. If I have a material that is on end of life, I cannot use for a high performance application, maybe I can use in a lower performance application. And this is very important to use. Reduce, to use as less materials as possible. That's why material additive manufacturing is so important. Reuse as many times as possible and recycle whenever it comes to the end of life. And then always do biotoxicity and ecotoxicity assessment, because at the end, no matter what we do and how care we do, many of the materials that we use go to the environment. And this is particularly important in the area of sensors and actuators. As I told you before, we will need trillions. We are 8,000 million people or persons in the planet, and it is expected that each of us will have between 12 and 20 dedicated sensors in 10 years from now. Okay, using the menos. So, whenever it is not possible, let's prepare particle-based inks, okay? The less materials we use, the possible, okay? And printed electronics always need conductors. If possible, the same system can be a conductor and also be used for a sensor and actuators. One of the most sustainable inks we have for conductors are graphene-based inks, okay, or other carbonaceous fillers. First of all, they are carbonaceous fillers. okay? They come out of carbon. They provide conductivity, okay? And for example, we can use more or less sustainable polymers like polyvinyl pyrrolidone, okay? With, for example, styrene, which is a solvent that directly comes from cellulose, okay? We have more or less sustainability in the solvent, we have more or less sustainability in the polymer, and we have more or less sustainability by using a carbonaceous filler that in principle has not so many problems, and other of the fillers that we can use, okay? And there, what we have to do is, first of all, to have the proper characteristics of the filler that we are going to use. This is important from 2 points of view. First of all, the functional characteristics that it will have. But second, the compatibility with the solvent and the compatibility that it will have with the polymer. One very clear example we come here. We use reduced graphene oxide and reduced graphene oxide doped by nitrogen. Very different. The surface area, one is near to 500, in the other one 200. The density is also different, and the electrical conductivity is double in the nitrogen-based modified graphene oxide than in the other one. By evaluating the graphene, also, the reduced graphene oxide has almost no defects, therefore the larger conductivity, but the other one, nitrogen-modified graphene oxide, has a higher level of defective structures. This is important because even for the same concentrations, that we prepare different concentrations of the materials to tune properly the viscosity, but you see that for the same concentration, this is, first of all, a huge variation in the viscosity depending on the concentration, what is normal, but for the same concentration, there is a clear difference in viscosity, an order of magnitude, depending on the fillers and the defects on the surface that I have used. That means that I can tune through concentration, but also affecting, obviously, the electrical conductivity of the material, or by the filler for the same concentration, not so much affecting the functional performance of the materials, but the printability that I am going to use. Again, I can tune the sustainability by the filler, by the solvent, and by the polymer binder. No more elements are needed, but also I can tune the most important parameter for processing, that is rheology, one of the most important, and the functional characteristics just by the proper selection or functionalization of the filler. I do not need so much problems, and there I have a tune of the shear resistance, as I say, in more than an order of magnitude, and a tuning also of the adhesion to the surface I can print, again, only by using the specific formulation, okay? We can go even further. We can choose the best of the solvents that we have, of the functional materials that I have, one of the graphenes, reduced graphene oxide, and we use carbomethyl cellulose, a fully green polymer binder, and a mixture of water and ethanol for improving the printability, adhesion, and solvent evaporation. And then I prepare different solutions from 10%, 90% graphene cellulose content to the opposite, 90 to 10. Obviously, by changing the graphene content, also there is a variation in the viscosity, that means the printability, probably not very suitable, the last with a higher graphene content for inkjet printing, but for screen printing that we are using here, we can maintain the printability by the proper mixture of water and ethanol, but you have a huge variation in the functional properties. And you can have from a dielectric for a high conductor to a thermoresistive to a piezoresistive. So you can have a complete system just by some carbomethyl cellulose, water and ethanol, and graphene. Basically, carbon and water everywhere. Of course, depending of the rheology, the structure of the line that you obtain is better or not so good. You have to, because we are not using any further materials than these three, but this is enough for the applications. It is great. And with 90% graphene oxide, we have conductive tracks, and as I say, by varying a little bit. You have here the printed lines, very compact, very interesting, independent of the graphene content. You have conductivity among the largest in the literature, all with environmental friendly materials and with no further addition. So we have the conductive tracks, but also if we go to the reduce from 90 to 70% of graphene just for the active layer, okay, what we have there is a very beautiful thermoresistive sensor that can perfectly measure temperature variation in a linear way. But if you go even lower, only for 30% graphene, you have a piezoresistive sensor. That means variation of the resistivity also in a linear way, up to 5% deformation, okay, with the same system. So huge contribution to the sustainability based on basically carbon and water. And you can implement in the functional point of proof of concept from kind of transparent electronics, an interactive window, okay, there to touch screens that you can implement in the, for interacting to your, basically touchpads that you can implement for the systems or implement into wearables, okay? Simple and easy. First approach, the same materials, particle-based with a sustainable polymer binder with a sustainable solvent. But will be better not to have particles. And there are not many possibilities, but there are some. And one of them are salts, ionic liquids in particular. Okay, that's a particular type of salts. We can get rid of all these particles, I work with fascicles, by substituting all of them by ionic liquids. We can have no piezoelectric, but piezoionic, magnetic, thermal, photo, and again piezo. Why? Because ionic liquids are wonderful, are like salts, anions and cations, high thermal stability, negligible vapor pressure, high conductivity, they are non-flammable, high viscosity and density. They are also great solvents, by the way, okay? And you can tune, by tuning the anions and cations, the functional response, but more important, the interaction with the solvent, if you use, or the interaction with the polymer. That means the stability of the functional ink and the rheology of the functional ink. And for example, here, biocompatible anions and cations for tissue engineering, photoluminescence for anti-counterfeiting, magnetic anions for magnetic sensors, more conductive ionic liquids for actuators and pressure, or also magnetic in this way, but with thermochromic properties. As you tune from the ionic liquids and the polymer, the interaction between the polymer binder and the ionic liquids, you do not need basically anything else. And this is also a big contribution to sustainability, okay? You have to choose the polymer binder and the amount. It can be inert, okay, or active. If it is active, it is okay, basically synthetic, but if not, silk fibroin, carrageenan from the algae, sodium alginate, or cellulose, okay? By anion type or cation type, you get the functional response. By tuning anion and cation, also the stability with the matrix and also the rheology, that means the compatibility with the processability. One example, piezoionic response. You see, we use a highly conductive ionic liquid into a polymer matrix. Now I will go fast, okay? 5 minutes, 6, okay? You have to control always the printed line, okay? As we have here, the structure has to be, if possible, compact. You make a study depending on the file content. Always have to evaluate the polymer matrix interaction and the thermal stability of the system, and in this case, electricity, the functional characteristics, and then you evaluate how the resistance of the materials change under applying cyclic deformation. And you see that it is proportional to the force and proportional to the deformation. And you do things as interesting as this: a fully transparent printable touch screen based on ionic liquid and whatever polymer you use. It can be alginate, it can be carrageenan, because in this case, the polymer is not active, it's just passive. It's the network that has to allow the proper interaction to the ionic liquid to let it move, but not enough mobility to get out, okay? And then another functional contribution to multifunctionality. Ionic liquids, most of them are antibacterial. That means that you have a high traffic surface, the surface that all of us touch, that also antibacterial capabilities, okay? And this you can apply, again, in a huge variety of things, always measuring deformation, and we have in the lower right, okay, for endoscopes or people going, working. This is the sensors that you implement everywhere. The same, just by changing the anion and introducing a magnetic particle. The same is exactly the same. Magnetic particle, no, a magnetic atom. Magnetic response is not high. You cannot compare with the nanoparticles, but it is high enough to have, for example, magnetoelectric response, as you see, and measuring the deformation of a material to a magnetic field. That means measuring indirectly the magnetic field, okay? Again, more or less, because not all of these are environmental friendly approach, based only in ionic liquids that are dispersed in a fully environmental friendly magnetic, polymer that is processable most of the times based in water. Humidity sensors, exactly the same, okay? The only thing that I have to take into account is the engineering of the ionic liquid that is going to provide the functional response. This is thermal constant, the constant temperature, varying humidity, when you see the thermochromic sensor. Not only is, in this case, humectochromic, sorry, okay? Then you can do the opposite. You can tune the anion so that you have the opposite. For a given humidity, it sends the temperature. As they are ionic liquids, they have anions and cations. Most of them, they are not only chromic, they are also thermoresistive. So you can measure also accurately the electrical resistance of the system. Photoluminescence, to give the same example, because it is right. Again, basically, I use, most of the times in the work that we are doing, we are using basically the same cation, but we are changing the anion with a luminescent particle. You can tune there, and this is based on alginate. Again, we make the interaction with the polymer, the stability over time, and you can have this beautiful luminescence particle that you can use for anti-counterfeiting, for example. I think that I have some example. No, it's not here. I thought that I have, okay? You see? Okay, you cannot see, and now illuminate with UV, and you can see. Or the same with electroluminescence or electrochromic materials, okay? So this is a nice possibility. The other one, more difficult. To make a material to sense is easy. To make a material to actuate is more difficult. Again, by applying a specific electric field, by using small anions and cations, apply a field, they separate. If the size of anions and cations is very different, okay? Anions and cations occupy different part of the polymer, and the polymer bends. Here you have a very beautiful screen printed actuators, okay, that can make cell sorting, soft robotics, or whatever it comes. More interesting even, you can do that. Sorry. An actuator that is also luminescent, to see who it is or what it comes. Again, alginate or carrageenan, environmental friendly, most of the time water or related solvent, and ionic liquid that controls fungibility, printability, functional response. As just to finish, The other approach is not to use nanoparticles and not to use solvents. This is the most of the most. And for there, you can prepare the materials with ionic liquids, but with photocoolable polymers. It is not so easy because sometimes the functional part absorbs part of the UV and the curing is not so good, but the UV-coolable polymer can be obtained. I go fast just to have some questions. It can be obtained, for example, from vegetable oils, okay, and these are the most interesting one, with performance basically the same as the synthetic ones, okay. In this case, sustainability doesn't lag behind high performance materials, okay. You prepare the materials.
So, Mendel, excuse me,
1 minute.
if you can sum up in 2 minutes, then we have a few minutes for questions. Thank you very much.
I will answer exactly in the same way as the other one, okay. I will go fast just to see the functional response. Of course, you have to check always the printability, but you get very wonderful 3D structures, okay, that you can, with very high quality and resolution, implement into whatever 3D structure you get. So, and the same for other applications, okay, electroluminescence, whatever. Challenges for sustainable digitalization. All the sensors have to be powered, all of them. We have to print also energy harvesting system or printable sustainable batteries, because the batteries that we have nowadays are not sustainable at all. And many of the batteries that we use are too high performance for the application. And this is an area of very, very important interest. One example to finish. For healthcare devices, we have sensors that sometimes have to be used 3-4 minutes. We need a battery that takes 2-3 minutes, and they can be thrown away or be degraded. Smart packaging, transportation, we need a battery and a sensor that can be recycled with the box, and it has to take 2 weeks, 3 weeks, the maximum, from China to Europe for delivery products. Or for smart agriculture, we need batteries and sensors that take 3 months, 4 months, what is a harvest season, okay? So very important to have that into account. And then to be able to integrate all of them. Multi-printable, multi-material systems that allow to produce not part by part, but the whole part of the materials. And we have here the battery with the communication system, with the resistive and humidity sensors, or in the obvious way. The battery, by the way, is the largest part, and the system is printed on the battery. So to finish, we are in the middle of a revolution that is made out of smart materials for the digitalization transitions. This digitalization has to be sustainable, and for that, we need sustainable sensors, actuators, compatible with printing technologies, okay? Thank you very much. It has been a real pleasure. Okay.
Thank you very much for this very impressive presentation and very educative, I think, for the applicants. Let me check the chat for questions. We have a couple of them. The first one from Maria. I think she asked about which is the important parameter for the stability of inks, and if you can give an advice to improve the stability of inks, I guess.
This is a very important question, of course, but there is no general answer, because the stability of the inks depends on the formulation of the inks. For example, when you have inks based of nanoparticles in a specific solvent, as it is, for example, the silver-based inks, there the only thing, because you have a high density material into a low density one, what you need for the stability is that there are not agglomeration. That means you have to prevent agglomeration of the particles, so that give a larger weight and a faster stability of the materials, okay? But it is very different, for example, if you use the ionic liquids dispersed in a polymer and a solvent. There you don't have those problems of stability because the interaction between the ionic liquids and the solvent prevent agglomeration. The dispersion is good. And the density of the materials is basically the same. So that means you have to take into account only two parameters, the differences in density of the materials and the interactivity into the different players, particle-particle, particle-solvent, solvent-polymer. And there you can control that in a relatively good way. In some cases, and in the case of nanoparticles, just in a solvent, due to this variation, sometimes you need the functionalization of the particles, but it's an additional parameter that involves more chemistry and less sustainability in a clear way.
Thank you very much. Another question from Natalie. What would be the relation between the surface tension between the ink and the substrate?
This is absolutely important. It determines everything. It determines, in a very, very important one, two things. Of course, at the end will be the addition of the ink if you are going to have a very clear and stable printed pattern, but more important, the definition of the ink that you are going to have. If you are going to have a line with a very, very good definition, or if you are going to have a line that is going to be not so perfect. And it will limit also, as limiting these two parts, it also limit the accuracy of the lines and the minimum resolution that you may have.
Okay, thank you. Another question about when you prepare a new formulation, a new ink. So according to the applicant, there are many factors that can affect the quality of the material and the ink. Do you apply design the experiment taking account several factors separately? Any advice in this regard?
Very important question, this. Very, very important. You know that we are making a transitions between researchers like me to researchers like you, okay? Researchers like me were more inspiration-based and a lot of going to the laboratory and try the things based on the knowledge, of course, that we have. Now we have a lot of information and even very, very interesting and important simulation algorithms, not just artificial intelligence algorithms that now is in fashion, but also intelligent algorithms. In any case, what you have also, that means that most of the time we already design more or less the ink, and we have a narrow spectra of parameters that can influence. So basically, we prepare the ink almost very good at the beginning, but we still have to fine tune it. And you always have a dominant parameter that it is there, that basically is the filler-filler interaction, filler-solvent interactions, and eventually polymer-solvent interactions. By tuning that, we have achieved basically, now is coming one paper for us, which is, I would say, impressive, because we have obtained with inkjet print, with screen printing, basically the same resolution as inkjet printing. And it is basically by tuning the rheology and the surface tension of the inks. But the main parameter is always the interaction between the elements, and nowadays you can simulate that pretty well.
Thank you very much. I think we have time for a last question. There are many questions. You probably can contact directly Professor Mendes.
Will be a pleasure. Always ready to support you guys in all the.
I can send you an email, yes. So the question is, could you comment on the exotoxicity of graphene? So I read a study about biodegradability of carbon-based materials.
Yeah.
Yes.
Very important question, really very important, because, you know, I am really concerned about that. It is not that I speak to you because I have to speak to you. Again, I am convinced of the importance, of the relevance of the work that we are doing, and I am convinced that printable sensors will go everywhere, from our bodies to our clothes to our environment, and we must know the end of life of these sensors. They have to be sustainable and they have to be not toxic, because, of course, nanoparticles are even worse than the microplastics that we are very concerned nowadays. Among the different particles, graphene by far is the best that we have. First of all, because it is graphene, and because it is carbon, okay? So by far it is the best. Graphene is being used for many biomedical applications. So that means that what we are careful with the handling, not breathing so much, and in the end of life are the best fillers that nowadays we can have. And even because they are structured, the 2D layer structures, from the point of view of the ecotoxicity and even from the point of view of the biotoxicity, it is much better than nanotubes, for example, because in toxicity, it is important the composition, but it is also very, very important the specific safe and specific area. Okay, so the reactivity that it provides to the given environment, and there are cases that are impressive. For example, titanium dioxide or zinc oxide, both are used for catalytic properties. But zinc oxide is, I think that is, I don't want to say but now, but it is between 100 and 500 times more toxic than titanium dioxide that it is not, okay? For the same particle size, okay? That's it, that it has to be studied in each case. The protocols exist, we know how to do that, and graphene is by far the safest of the materials we handle with. Mm-hmm.
Okay, thank you very much. This was the last question. Thank you again for your participation.
Thank you for the invitation. It has been a real pleasure.
Welcome. So now we have a break, 1 hour for lunch. So we'll come back in an hour. Thank you very much. Bye-bye.